Wait, so let's define our symbols. We've got A is greater than B. And so this, and then we've got A is less than B. And so there's a lot of different ways people think about this and try to remember these symbols. I think probably the one that's sort of most popular or common is to think about this symbol as some sort of mouth. And so, you'll see teachers that'll like draw little teeth on it or whatever. If you're of a certain vintage, you may remember this as sort of like a Pac-Man figure. And draw it like that, and it's eating the larger thing. All right. So whatever you want to think about it as, it's certainly a mnemonic way to think about it. That we're wanting to eat the larger number. It can be a little confusing for some students because if you look at this way, then we're eating the larger B, but we still have to read this from left to right. So we're saying that A, and then this is eating the larger B. I mean, you have to put this in some sort of like inequality context. And so since we're addressing the A first, for some students, this can be a little confusing because they're thinking about what's larger, they're thinking about what's greater, they're thinking about the bigger one. B is bigger than A, but that's reading it from right to left. So just be aware of that. The little eating mouth toothy mnemonic thing is helpful, but for some students they're going to struggle with that context. We can look at problems like this, say 172. So which of these is larger? And this goes back to what we've been talking about already in terms of place value and in terms of digits. There are going to be students who are going to look at this 7 and look at this 1, and they're going to say, well, the 7 is bigger than the 1, so the 72 is larger. And now you have to explain, well, the 7 is a larger digit, but the place value of the 7 means it's going to be less than the place value of the 1. And we can also explain this by saying, well, this 7 is in the tens place, so if you look at what's in the tens place, we could think of this as being 10 in the tens place. Now, 10 in the tens place is the same thing as 100, but by using a consistent place value, in this case the tens, we can see that the 10 tens is greater than the 7 tens, the 100 is bigger than the 72. So again, students have to be able to use digit and place value in concert to really understand a lot of these fundamental concepts around number and numeral. This gets a little bit more confusing once this sort of gets like decontextualized and we start to move the place values down a little bit. So if we were to take the same sort of analogous problem, and let's say that we were comparing 0.01 and 0.0072. Now, this is effectively the same problem, right? And so you can see that all we've done is we've taken this decimal point and we moved it 1, 2, 3, 4 places to the left, 1, 2, 3, 4 places to the left. So we've divided this by 10,000, right? So the inequality is going to remain the same. But for students, this 100 and this 72 is going to be a lot more intuitive than this 0.01 and this 0.0072. But we can explain this sort of the same way. We could add on these zeros and then say, well, let's look at these places. We're now in the tens, hundreds, thousands, 10,000s place. So we've got 100 10,000s or 72 10,000s. And we get into fractions, we'll talk a lot more about talking about same size pieces, quote unquote. And so by using the same idea of finding a consistent place value and then making the comparisons from there, it'll make things a lot easier for students to make these comparisons. If we take these zeros off, again, this looks like we're comparing a 1 and a 72, and that's definitely not the case. We can use number lines to show inequalities as well. If I have a number line like this, So let's say we've got A and we've got B. We've got our 0 here. So, we could ask students, which is greater, A or B? And one of the things I like about this question is because a lot of students are going to want to say, well, what's the value of A and what's the value of B? That they've seen inequalities in terms of strictly quantitative comparisons, just comparing numbers, and not really thinking about what inequalities really mean, and especially in a different context other than a numerical context. A lot of students won't struggle with this, but there are going to be some that will look at this problem and they would not have thought about inequalities this way. In fact, you might be thinking, I've never thought of inequalities this way. The number line increases to the right and decreases to the left. So we know that in this case, B is greater than A because it is further to the right. It's further along. It's moving in the direction of the positives. It's moving in that increasing greater than direction. So without knowing anything at all about the value of A and B, we know that B is bigger than A. And in fact, I could take A and I can move it around and B remains greater until A is the same place as B, and then they're equal to each other. And then if it keeps moving, then A becomes larger than B. So we can use number lines to illustrate and recontextualize these problems around inequalities. This is really helpful when we get to problems involving negative numbers. So if we were to say 7 and 4, which is greater, well, we could put the 4 here, we could put the 7 here, and we could see 7 is greater than 4 because the 7 is further to the right. But if we ask students which is greater, -7 or -4, especially right after looking at 7 and 4, a lot of students are going to want -7 to be greater than -4. Why? Well, because 7's bigger than 4, so why wouldn't -7 also be bigger than -4? A lot of students are also going to be sort of conflating this with absolute value. The 7 is further away from 0 than the 4, which is true here. And if we were to look at -7 and -4, well, the -7 is further away from 0 than the -4. And so the absolute values remain consistent. So if they're thinking about absolute value in this case, then the -7 being greater makes sense. However, if we draw this on a number line, so we've got our 0, 1, 2, 3, 4. So here's my -4, 5, 6, 7. Here's my -7. So here's my -7. Here's my -4. And the same rules still apply. This is still getting larger as it moves to the right, and it's still getting smaller as it moves to the left. So this is hopefully irrefutable evidence that the -4 is larger than the -7. Some of you may have done or remember problems like this where you were solving problems with inequalities and you had these things where when you multiplied or divided both sides by a negative, you had to flip, quote unquote, the inequality symbol around, and this is why. So you'll see that these numbers don't behave, the inequalities don't behave the same when we change from positive to negative, that the inequalities sort of move in the other direction. Well, sort of, they actually do. So for a lot of students, this is a very counterintuitive thing. It doesn't make an awful lot of sense that how come 7 could be bigger, but -7 isn't. And so this number line model helps put that into context. That's pretty much all for section 1.3, and this is a pretty short one. Make sure that you know what your inequality symbols look like, and make sure that you can model these using both base 10 blocks and number lines. All right, thanks. So I just wanted to leave you with this last quick problem here. A positive number is always greater than a negative number. How can we use our number line model to show, explain, or refute this claim? So this is a broad statement. It's sort of an abstraction on what we've talked about. So how could we use the model that we've looked at? So think about this problem, and then we can talk about it in class if you have any questions. All right, thanks.